All right, welcome everybody. We got about 2 minutes to go before showtime. Hope all is well. My name's John Barba, and to my left on the share screen is my good friend Bruce Marshall, who'll be taking this over when we get started. Figured if we're going to get someone who knows about combustion analysis, let's find someone who really knows about combustion analysis, and we got the best there is in the business to share that with you today. So, okay, so we got about a minute before we get started, so we're going to let everybody roll on in. And hope everybody's doing well out there. I've got 133 people out there right now, kind of going up, a few more, a few more, a few more. That's all good. That's all good. Anyway, so I hope everybody's doing okay with all the craziness in the world and the virus and all that stuff. And hopefully we'll get back to normal and get back out there and doing some work and making some money and leading a normal life. Let's keep our fingers crossed. Anyway, alrighty. Let's get this show rolling, I guess. We're just about at noontime, depending on which clock I'm looking at. I do want to welcome everybody. Thank you for joining us on this session on combustion analysis. This one's going to be a little bit different than what we normally do because basically we have a guest speaker. And as I said, I've known Bruce Marshall for an awful long time, and he is the official title holder of the smartest man I know. I every time I listen to Bruce, I learn a lot about a lot of things, and it's my great privilege and honor to have him here with us. Bruce has been retired for the past a couple of years now, right, Bruce?
Yeah,
Yep.
2.5 years.
2.5 years, and we figured, well, let's get him back in the arena. Don't want the man getting rusty, right? But I guarantee you're going to learn a lot about combustion analysis today and how to do it the right way, the importance of it, and the right equipment to use. And again, as I said, Bruce is the best in the business that there is at this. Just so we have Noel Kelly says, Bruce who? Just so we all know how this thing works, do me a favor, for everybody who's out there, just to make sure you can hear me, on your control panel, there should be a little cartoon balloon with a question mark on it. Folks, that's going to be how you ask questions. So if you could do me a favor, just click on that and then type in a hi, hello, how are you? Anything like that, so I know A, that you know how to do it, and B, that you can hear me. Okay, so oh boy, those are coming in fast and furious. Excellent, terrific, terrific, terrific. So good, thank you very much, guys. Excellent. So with all that in place, that's all really good. The other thing I want to remind you folks to please make sure to do is to treat this like you would treat a classroom exercise. All right, like just pretend we're in a classroom together and keep a pen and a notepad right in front of you, okay? And take notes, write stuff down. Pretend you're in a classroom with us, because you can see us, but we can't see you. And webinars are funny this way. Webinars are really easy to zone out on. You can check Facebook, you can do other stuff we don't really know. But you're investing an hour here to be with us, so do the very best you can to stay engaged. And I found that note taking is the very best way there is to do that. Okay, everybody will be getting a link to a recording of this webinar tomorrow, so you can review it as many times as you like. So you'll have all that available to you. But to get the most out of this session, please make sure you take some notes and ask some questions. That's the other important thing. Type your questions in here. We'll be taking a break every couple of 3 slides, to catch up and see what questions you might have as we go along. So with that, I am going to do the merciful thing and kind of shut the heck up for a little bit and turn the screen and everything over to my good friend and longtime colleague and one of the smartest man I know and one of the best trainers I know, Mr. Bruce Marshall. Please give him a warm Take-O Tuesday welcome.
Great. Well, thank you, John. That's that was pretty good introduction. So I do appreciate that. Let me see if I can figure out how to make this all work. I have to do a couple of things. Let's see. This I want to show my screen. So let's see. This works.
There it is.
There it is. Okay. So do you have? There we go. Do you see the title screen?
We are rocking and rolling.
All right. Great. Well, then here we go. So Combustion analysis, it's testing, not guessing. The problem with guessing is that sometimes you guess right, and that just enables you to guess some more. It's not very scientific. These are some, give you an idea, these are some pictures of why we do combustion testing. So we don't do things like this, or this, or this. This one was up in Maine several years ago, and it's one of the worst things I'd ever seen. This modular house that's on its way to being black. So we do combustion testing so these things don't happen. I want to take a little step back into the past, and here's an idea of the kind of boilers that we see. Unfortunately, there are still quite a few of these in existence today, but these were either originally coal-fired boilers that were converted to oil, or first-generation oil boilers. And we're talking about, the late 40s, early 50s. Interesting, on the picture on the right, if you look at that picture, it's got, on the right-hand side of that boiler is an ennitrol. And for some of you folks that have been around for a while, you remember the ennitrol was a very early electronic device to give you outdoor reset, to make a boiler a little more efficient. It was the idea of this was to make the boiler weather responsive. It was a really good idea, well before its time. We're talking about the 70s. Taco, in fact, incorporated that into a product called the Mastermind. It was basically the same product. So an early way to improve efficiency of boilers. But that was the past. Today, this is the present, and boilers obviously have shrunk in size in the name of efficiency. They've gotten a lot smaller than they were. They're not as heavy as they were. The water content has gone down. And this is an example of cast iron boilers that we have today. So we call this the present. And also in the present is the wall-hung condensing boilers. We have many of those. Those have been around for several years. Many different configurations and different types of wall-hung condensing boilers, but we will consider that the present and actually the future. This is where the industry is going. And again, all in the name of efficiency. Well, stepping back into the past again, if you remember those cast iron boilers had those big doors on them, big wide open doors. And the idea was that you could shovel coal in there, so you needed a big door. And if we did any combustion testing back then, and we didn't do a lot because really we didn't care that much about efficiency back in those days. Oil was cheap, gas was cheap. Efficiency really wasn't a big deal. We still did combustion testing. But what guys used to do a lot was open the door to take a look in. We were all flame heads, and we liked to see the fire. You had to see it. It was very fascinating to see a fire. Well, one of the things you were doing when you opened that door was you gave that fire a big gulp of oxygen, which made the fire actually pretty good. It was a really nice looking fire. Of course, as soon as you closed the door, it went back to having smoke, which you couldn't see. So opening the door was very counterproductive. Well, boilers today don't have doors. You can't open the doors. There's nothing to see, which is a good thing, which really shows the need for testing because you can't see anything. A step back into the past was the old back rack wet kit. And this is what we used back in the 70s and 80s. And the kit consisted of all these items you see on the screen. We'll go over them one by one. The smoke tester was very important. In fact, this is the first test that you should make, especially if you're testing oil. You want to make sure there's no smoke because obviously the smoke means you're making soot, which of course your readings are going to be off the chart. But if you're using an electronic analyzer, you really don't want to put any smoke into that because that's going to really affect the performance of the machine. So the smoke test is really the first test you should make. And these smoke testers are still in use today. Although some of the electronic analyzers will do smoke, they will analyze the smoke electronically. My thoughts on it have always been it's still a good idea to use this old-fashioned method because it still works pretty well, and you really don't want to put soot particles into your analyzer. So with the smoke tester, you would take a sample of the flue gas, and it would take 10 strokes of the handle. You had a little spot of paper that went into a slot, and then you would compare that little dot that you get to this chart. And this was from 0 to 9. Obviously, we're looking for 0 smoke. So you take your test, and then you compare it like this guy's doing here, and you want to make sure that you don't have any smoke. You'd match it up to one of those circles, and that'll give you an idea of what number smoke you have. If you have number 9 smoke, you've really got a problem. You're really looking for 0. You're looking for 0 smoke. So if you had any marks, you would make an adjustment and then take another test and try to get as close to 0 smoke as you possibly could. Another part of the kit was the FireRite CO tester. And it came with this little squeeze bottle. And you take your probe and put it into the test hole and pump the squeeze bottle 18 times, and you put a sample of the flue gas into the liquid. And what would happen is the liquid would raise. You'd start off at 0, you'd zero it out, and it would expand inside the tube, and then you would read across the top of that the column of fluid, and that would give you your reading of what the percentage of CO2 was. In this case, you're looking at 9% CO2, so you'd read it right at the top. And then finally, you needed to check the temperature of the flue gas. And you see here, we're approaching 800 degrees. That was pretty common back in those days to see very high stack temperatures. So you had to do these 3 things: test the smoke, check the CO2 level, and see what the thermometer gave you for stack temperature. This was the calculator. It was a little slide rule calculator that you would, once you got your stack temperature, you wanted to check the net stack temperature. The next net stack temperature is whatever number you saw on your thermometer minus ambient. And this was the black numbers in that little window were in 50-degree increments. So 50 degrees is a pretty good average of what the temperature was in the building, and you'd get close enough. So whatever your stack temperature was, you'd subtract 50 and put that in the window. And then the green arrow, you would go against the chart on the left to the numbers you got, the reading you got on your CO2 analyzer, and inside the window would tell you what your combustion efficiency was. We're looking here at 79.5% with a total stack loss of 20.5%. So that's pretty good. If you could do that back in those days, you were doing pretty good. If you could get to 79% with that old equipment, that was about the best you were going to get. You also had different cards for different fuels. In this case, we're looking at on the top, you had a slide card that was for anthracite coal. That'll give you an idea of how old this was. You had one for natural gas. You had one for kerosene. So all these different fuels had different numbers. So you could analyze different types of fuel by changing these cards. Pretty archaic by today's standards, but it worked, and it got you where you needed to be. Finally, you had to measure the draft. That was your last thing, is measure the draft in the appliance. Find out what the draft is, and you see on the upper right underneath the word draft, was the draft gauge that came with the FireRite kit. And there were other types of gauges that you could use, a lot of different things that'll get you to the same place. But this was part of the kit. So that was the past. Well, today, the present, and the future, all of those things are combined into an electronic analyzer that'll do all of those things, all of those functions that the FireRite kit did. And there are many different manufacturers of combustion analyzers. This is Backrack, and came out with the original FireEye kit way back when. This is Backrack's version. Here's Testo. Testo has a nice one. Here's Wohler. Wohler has several. Many different manufacturers out there of combustion test equipment. And what do you want to spend? How much do you want to spend? You could go with very inexpensive ones, or you can get very expensive ones. It depends on, do you want a Chevy or do you want a Mercedes? It's like, what do you want it to do? I think one of the things that you need to look for when you're shopping for an analyzer or buying an analyzer is the serviceability of the unit. What type of service does it need? They all need service. How often does it need servicing? How easy is it to change the your sensors? And do you have to send it away? Do you have to send it out someplace? If you have to send it out someplace, how long is it going to take to get it back to you? I think those are important questions that you have to ask, because this is a tool and you need the tool. You can't do your job without the tool. So I think if you're shopping, that's something that you really need to it's a question you need to answer. What kind of service it needs and how fast can it get it back to you? So let's compare analyzers to your chemical wet kit or your electronics. So the wet kits are slow. Remember I said you needed 10 pumps on the smoke tester and 18 pumps on your CO2 analyzer. That all takes time. Very time consuming. You don't have the luxury of time with today's equipment. Cumbersome, hazardous chemicals, sure, that red stuff in there is potassium hydroxide. You really don't want to get that on your skin. And disposal of it is a problem. You really shouldn't dump this down the drain either. So disposing of it is an issue. It's old technology. This is from the 30s. So we're talking about ancient technology that's almost 100 years old. If you put your bottle in upside down, the fluid will eat the seals on the bottle and you'll have leaks and it'll make quite a mess. I can tell you, I've seen this up close and personal. There are many more opportunities for human error, because now you're depending upon the integrity of the technician to write the truth down on that little piece of paper, that little slip of paper that you're supposed to leave on the job that's going to tell you the numbers. And if he doesn't like the numbers, well, he can make up some, that look a little bit better. So there are a lot of opportunities for human error. But the biggest issue is that it only takes a snapshot of a moment in time. That particular moment when you're doing the test, it just bang, there it is. That's what you're getting in that particular moment. Compare that to your electronic analyzer. It's the difference between a snapshot and a motion picture, because now you can see the changes that are occurring as you make them. So you're getting real-time analysis of what you're doing. You can make your adjustments and look right on the screen and see exactly what's happening. They're all compact, very compact. There's handheld models, in fact. When these first came out years ago, they were in suitcases. Now today, they're very small, like about the size of an electronic meter. Handheld small units that are very compact. They have communication ability. It's amazing what they can do today. They can communicate with your cell phone through Wi-Fi. They can communicate back to the office. They can send information through the internet. It's just incredible, the advances that have been made in the last few years in this equipment. The printed record is really, really important. That's your get out of jail free card. That's your, you do a job, you make your adjustments, and you set the equipment up, and you print a printout of what you have, and you take that back with you, and that goes in the file. Leave one on the job also. And 6 months from now, something happens. Well, that's out of your control. But what was in your control was that when you were there, and that's your printed record that says you were there, and these are the numbers that you got at that particular day in time. What happened in between then, that's not your problem. But it's very important in today's litigious society. Everybody wants to sue somebody. this is your get out of jail free card. So that's pretty important. Most of your units will give you everything on the same screen. Some of your lower end, less expensive models won't give you readings simultaneously. You'll have to scroll through each screen to get different numbers. But most of your higher end equipment will give you everything on the same screen all at the same time. That to me that's a good feature. And of course, multi-fuel testing. How many different fuels do we deal with on a daily basis? We got fuel oil, we have biofuel, we have kerosene, we have propane, we have natural gas. I mean, we have all these different fuels. We have pellet stoves, all these different fuels, and that we, on any given day, we might run into 3 or 4 of them. So you have to have the ability to test any of these, and your analyzers will do that for you.
Hey, Bruce, I got a couple of questions for you.
Sure, fire away.
This one's actually, I think you kind of touched on this a little bit. This one's from Alexander Sival. I hope I pronounced your last name right, Alexander. Which analyzer would be a good option for a Chevy to start off with if we've never done combustion analysis before?
Oh boy, I would, not wanting to get into promoting one brand or another. If you go into Google and you just put in combustion analyzers, you're going to see a range of units. I just did this morning, and I saw one for $392, and I saw one on the other end of the scale for $3,000. So you've got to decide: do you want something that is going to last for a while, or do you want one that you're probably going to throw away in a year or two and have to buy another one? I think that's really how you have to look at it. You get what you pay for. I hope that answers the question. I don't like to promote one brand over another. I don't think that's a good idea. That's not why I'm here. But I think you look at, if price is always an issue. That in every phase of what we do, price becomes an issue. But just keep in mind, you get what you pay for.
Very good. I hope that answers your question, Alexander. Another one from Floyd Holmes. Is there a big difference between K1 and number 2 oils when it comes to efficiency?
Oh yes, very, very much so. There's your testing is going to be the same. Your testing is going to be the same. You can get good numbers with your kerosene, but it's definitely a different fuel. It's a lighter fuel, so it's all about BTUs. You can get your combustion efficiency to where you want to be with just about any fuel, but I think again, the chemistry of the fuel is a little different. So I think that answers that question. The chemistry of the fuel is different between kerosene and standard fuel oil, or even biofuel. It's all different. Your analyzer will take all that into consideration when you select the particular fuel you're testing.
Very good. And one last one from Avanish Ray. What is the best method for analyzing combustion efficiency, measuring CO2 percentage or O2 percentage?
That's either one will get you to where you're going to go. It depends on the analyzer you're using. Most of the analyzers today are measuring O2. Either one is going to get you to where you're going to be. In fact, a lot of the analyzers will give you both readings. It's going to give you CO2 and O2. One isn't any better than the other. They both get you to the same place. You have different numbers. In fact, we're going to look at that a little bit later on. Towards the end, I'm going to give you some examples of the numbers that you're trying to get. You're looking to get higher numbers of CO2, up in the 10 to say 12% CO2, and in O2 you're looking for lower numbers. You're looking for say 5 to 7%. So, but you'll see that a little bit later on. One is no better than the other. They both get to the same place.
Very good. All righty. Continue, sir.
Okay. This is what combustion is all about. We call this the circle of combustion. You need fuel, you need air, and you need ignition. You need all three The circle has to be complete in all phases of your operating cycle, startup, shutdown, and while it's running. You need all three. So what are we testing? We are testing this combustion. So some reasons why it's so important. Well, efficiency, that's a good reason. We want to make the equipment as efficient as possible. And for fuel savings, if we can increase the efficiency, we are increasing the fuel savings. We want to burn as much of the fuel as possible. Safety is pretty big. We don't want to make carbon monoxide, and all fuels will create carbon monoxide. So it's toxic to humans and pets, and so we really need to minimize that. So combustion testing is very important from that perspective, just from a safety perspective. And of course, environmental measures. Carbon monoxide and nitrogen oxide are hazardous to the environment. CO2 is a greenhouse gas. We all know that, and so we really need to minimize these environmental hazards. And then finally, preventative maintenance. You can identify a problem before it becomes a problem. Reduce breakdowns in your equipment. So it's very important. I marvel at the fact that there are still people out there working on equipment that don't have a combustion analyzer. And I just, when I was still working, I would be on the phone with people and I'd ask a question like, what are the readings on your analyzer? And I have silence on the other end of the phone. It's like, what are your readings? Well, I don't have one. And it was, I felt like hanging up. I mean, what do you say to somebody that's working on equipment? I got a phone call from a guy one time that wanted to know what he should set his condensing boiler at. And I said, well, what are your readings on your analyzer? He said, well, just tell me what's the normal set. I said, what's your analyzer? And he didn't have one. I mean, you can't work on this equipment without an analyzer. In fact, you shouldn't even be allowed to buy one if you don't have an analyzer. It can't be done. Efficiency is based on how much energy is in the fuel, how much is not being used, and that's where your net stack temperature comes in. How much of that energy in the combustion process is being absorbed by the appliance, and how much is going up the chimney. And then finally, it's the percentage of O2 or CO2 in the flue gas. The flue gas is how we make heat. It's not the actual flame from the fire. It's the flue gas that's passing through the appliance that's transferring its energy from the flue gas to the medium on the other side, whether it be water or air, however, whatever the medium is, we're transferring that energy. We're taking it out of that flue gas and transferring it into the medium. And we want to get as much as we can out of that flue gas. And this is where stack temperature comes in. Your net stack temperature is the flue gas minus the ambient. The ambient temperature is the air that we're breathing, or the air that the appliance is breathing. Remember, on that old kit, you could just do 50-degree increments of the temperature. Well, today, your analyzer knows exactly what the temperature is in the room, and it will give you that net stack temperature right down to the 10th of a degree. So it's very, very accurate. So what we're looking to do, we're looking for the lowest possible stack temperature, and that's going to tell you exactly how much energy we're extracting. Now, in oil, we don't want to condense. Up until recently, oil has had a fairly high sulfur content, and now today we have the low sulfur oil. Back when we had a high sulfur content oil, you really didn't want to condense that because you're creating sulfuric acid. That was one of the drawbacks to condensing oil equipment back in the day. Now today, with the low sulfur oil, we might see the advent of more condensing equipment with oil because the sulfur has been removed. But years ago, it really wasn't possible. This also can be a problem with a cold start boiler with no boiler protection, because if you have a cold start boiler, it's in the middle of the summer, the boiler is at ambient temperature, and you start it up and you start doing your combustion testing. Until that boiler warms up, if your circulator is running, you're putting cold water down into that water side, and you've got the fire side with your higher temperature, and you're condensing. You're condensing in the flue passages, which is not a good thing. So it can be boiler protection is really simple. You hold out the circulator until the boiler gets up to temperature. But if there's no protection, then this condensing, and again, this is with oil, that can be an issue. This is an idea of what it looks like when you have flue condensation problems in your stack. Your flue gas is condensing in the pipe before it gets out, and the products of the condensation is running down the stack. This next picture is this is a year-old job. I did this job and came back 1 year later, and this is what I saw. And I remember we had great numbers. We were approaching 90%, like 88% efficient. We had low stack temperature and great efficiency. Well, wow, whoop-de-doo, look at what I did. I did this, and I came back a year later, and this is what I saw. And what we ended up doing was we had to sacrifice some of that efficiency by raising that stack temperature to stop the condensation. This was a 1 year-old job, so you don't want to condense in the chimney. So here is again back to our analyzers. What we need to do, we need to check our draft, our breaching and over the fire. We need to check for smoke, and that's with fuel oil. If we do testing heating oil, we want to look for smoke or no smoke. Zero smoke is our goal. We want to minimize the excess air, and we do that by testing the O2 and the CO2. Either or both will tell you the presence of excess air. And we want to look at stack temperature. We want to look for carbon monoxide, and again, we want to minimize that. And then today's equipment has the ability to test for NOx and SOx, nitrogen oxide and sulfur dioxide, which are both greenhouse gases. They're toxic, and so some of the equipment, not all, again, some of the equipment is calibrated to test for that. Any questions so far, John? How are we doing on the questions? Anything coming in?
I got a couple more. Got a couple here for you. What is the best way to adjust the stack temperature?
If you want to, if you want to raise the stack temperature, your best way is to add more air. By adding more air, you're going to do several things. You're going to increase the volume of gas. You're going to increase the stack temperature. But the byproduct of that is your efficiency is going to go down. Unfortunately, that's the byproduct, but sometimes it's necessary. In that slide I showed a couple of pictures ago, that chimney that had all the condensate running down, that was how I remediated the problem. I had to sacrifice some of that efficiency, and I had to lose some of it to raise that stack temperature. So the best way is to add air.
And to go the other way would be to remove air, obviously, right?
Well, yes, if you remove air, obviously we're trying to get as efficient as possible. So by lowering that excess air, by lowering the air and keeping within the parameters that we're looking for, our efficiency goes up. But again, there's some cases where you just can be too efficient, and again, I'm really talking about fuel oil. That's because you still don't want to condense fuel in your chimney. Mm-hmm. Now, if we're talking about condensing gas equipment, well, that's okay. So we want it to condense.
There you go. Couple of other questions regarding excess air. One is a recommended excess air percentage, and what's the optimal excess air percentage, etc. And is there a minimum stack temperature for oil? Those are kind of three questions, but two of them are the same. So
yeah, okay. The number, I think you're trying. You should try for 7 to 9% of your O2. If you see higher than 9%, you start getting into double digits. That's excess air. That's too much. You really want to shoot for 7 to 9% O2. Now, what was that other question about? Minimum stack temperature on
for oil.
on oil. I would say I would not go below 300. I would try to keep it above 300. If you start 300, 325 in that kind of range, even up to 350. 350 would, to me, 300 to me would be your absolute drop dead minimum. I wouldn't go below that, because keep in mind, if you're testing at 300 in the breaching, or it just as it exits, as the flue gas exits the appliance, by the time it gets up into the chimney, it's probably going to lose 40, 50 degrees. And even more so in the winter. So even though you might be 300 at where you make your test, by the time it gets up into the chimney, now it's down into the 200s, and that's where it's going to start to condense. So 300 is your minimum. 325, 350 is probably where you should be with fuel oil.
Okay. A couple more about, again, excess air. What would be the optimal excess air? How to maintain 0% O2 percentage in the stack so that we can optimize heat losses? I mean, I guess what Jane is it possible to optimize the O2 percentage to 0?
Oh, no, my goodness, no. No, if you can't do that at all, you're never going to see 0. Again, I think if you can get to 7 to 9%, is 0 doesn't exist. You're never going to get to 0. It doesn't exist.
Mm-hmm.
One of the things that you will see, especially in older appliances, if you've got an older boiler, let's say a 15-year-old cast iron boiler, you're going to have a hard time getting that excess air down because of leaks between the sections. It's just the fact of life. You've got the asbestos rope, or whatever the sealing is between the sections, gives out over time, and it's air leaks. It becomes air leaks, and since it's a negative draft appliance, it's pulling in air from the area around the boiler. So there's a point at which it's just you've done all you can do without stripping the boiler down and repacking everything, which you're not going to do. You might see higher excess air numbers, and there really isn't a lot you can do about it. It is what it is. Ideally, you could see have a new appliance. You test it today, and you get great numbers with the excess air. Come back in 3 or 4 years, and the numbers, what's changed? The excess air has gone up, and it's because you've got air leaks coming into the boiler, which you really can't do much about.
Mm-hmm. Gotcha. All right. A couple more questions here, and then we'll move on. Can you insulate the stack to help reduce the possibility of condensing in the stack?
Yes, you can. You can do that, but geez, there are better ways to do it. Just raise the temperature. It's just so much simpler. Yeah, you could go to all that trouble of insulating the stack, but you're really not going to. It's not going to help you that much. Your best bet is to raise the temperature, rather than to try to keep the temperature in the stack. I wouldn't do that.
Okay, good. And one last one here. Before we move on, should a chimney cap be always installed?
Oh, absolutely, absolutely. For several reasons. You don't want rain coming down your chimney. You don't want critters coming down your chimney. I found that out the hard way a few years ago. I didn't have a chimney cap. Had some squirrels come down and have a party in my living room. So
it was a short-lived one, I would think.
Yeah. Well, it was. They made it down, and they got through the doors and got into the house. And they had a party. So yeah, always chimney caps, absolutely, always.
All righty. Well, we'll get some more, but we'll hang on to those. Continue.
Okay. This is where we take our test hole. We drill our little test hole in the pipe. Location is very important, and you'll see in the upper picture, you see that little flashing red dot in the stack. Well, we want to get away from an elbow. So without getting into hard, fast numbers, 2 flue pipe diameters. Whatever the diameter of the flue pipe is, 6 inch, 7 inch, two of those from the elbow. And the reason for that is that turbulence happens at elbows. And this is called fluid dynamics. It's kind of the same reason you put an air scoop 18 inches away from an elbow, because of the turbulence that occurs in the elbow. Well, the same thing happens with your flue gas. You want a nice laminar flow of your flue gas, and if you get 2 flue pipe diameters from the elbow, the flow straightens out and you'll get a good sample. The other location on the bottom is the draft regulator. You want to be before the draft regulator at a minimum of 1 flue pipe diameter from that draft regulator, because that's a big hole in the pipe and it's just gulping in air and it's going to throw your numbers off. So you want to be two away from an elbow and one diameter away from your draft regulator. It's the way you take your test. Ideally, you want to be as close to the exit of the appliance as you can get. In this case, we're looking at a condensing boiler. We made the hole right there where the PVC joins the appliance. That's about as close as you can get. And of course, we're before the elbow, so we're not worried about the turbulence. So you really want to be as close as you can to the exit. So what are we measuring? Well, remember, O2 or CO2. We're doing either or both, and we're looking for the percentage in the flue gas. In a perfect world, wouldn't it be nice? A perfect world, everything would be good. Everything would be everybody would be happy. And if we had perfect combustion, we take fuel and we mix it with air, which is comprised of oxygen and nitrogen, mostly those 2 things. You've got a couple of other things in there, but it's mostly oxygen, a little over 20% oxygen and 78% nitrogen. And we have perfect combustion. We burn 100% of the fuel, then we would have left over CO2, nitrogen, which is inert and does not burn, and water, H2O. That would be wonderful if we could do that. Unfortunately, we can't. It does not exist. Neither does perpetual motion. So we don't have perfect combustion. We have incomplete combustion. So we still burn the fuel with the air, and we still have the CO2 left over. We still have the nitrogen left over. We still have the water left over. But now we have O2. We have oxygen. We have CO, carbon monoxide, and we have HC, hydrocarbons. That's a nice name for soot. And we have all 3 of those in addition to the okay things. So the similarities are carbon dioxide, nitrogen, and water vapor. These are similarities. Well, the differences are going to be the presence of CO, the presence of unburned gas or soot, and the presence of excess air. So these are the things that we need to minimize. This is what we're going to try to minimize, and when we do our combustion testing, we can see exactly those kind of numbers that we're looking for. Excess air. I know there were a couple of questions about excess air, so I knew I would get to this eventually. It lowers your CO2 and it increases the stack temperature. So again, if you want to increase the stack temperature because you don't want to condense, add more air. Increase your excess air, add extra air to it. Now, in the process, you're going to lower the CO2, which of course is going to affect your efficiency. Now, by adding excess air, you have now increased the volume of gas. You've got your set amount of flue gas and you've added some air to it. So you've increased the volume of what's going up the chimney. Well, that increases the velocity too. And of course, along with it, your stack temperatures are going to go up. As the stack temperatures go up, the efficiency goes down. Sorry, but that's the way it is. That's the byproduct. You're going to sacrifice some efficiency. Heat exchangers need time to absorb the heat. The longer that the flue gas can stay in the appliance, the more heat will be extracted. One of the reasons why your 3-pass boilers are so efficient, because that flue gas stays in the appliance longer. So if we can keep, and by the way, this is one of the reasons that we do that draft test. When we're looking to adjust the draft, we want to keep that draft down to slow that flue gas down from whistling through the appliance to keep it in the heat exchanger longer. So the simple fact here is the longer the gas stays in the exchanger, the more heat it extracts. It's that simple. Excess air has everything to do with not only the efficiency, but then that stack temperature. These are some numbers, and they're by no means hard and fast. They're just typical readings, and that you're looking to get with different appliances. So here it's an atmospheric gas-fired boiler, just a simple gas-fired burner. Could be a boiler, could be a furnace. We're looking at, and I'm being very generous here with that 75 to 80%, by the way. That's really generous because you're really probably not going to get that 80%, but it's possible. We want to look for 7 to 9% O2, 6.5 to 8% carbon dioxide, CO2. Stack temperature, anywhere from 325 to 500. Older appliances, be very common to see 500. And draft, negative O2 to negative O4 inches of water column, O2 over the fire, O4 in the stack. We're looking for those kind of numbers, and you can adjust to that with your draft regulator. And carbon monoxide, we want to see less than 100 parts per million diluted, less than 100 ppm. Now this is again with atmospheric draft gas-fired burners, just a simple, nothing fancy, just a simple gas boiler or furnace with no atmospheric draft means it's hooked up to a chimney. Now with a draft-induced gas-fired burner, our efficiency is going to tick up a little bit. We get up into the low 80s. Our O2 numbers are still pretty much the same. Our CO2 numbers are still pretty much the same, but you'll see that our stack temperature is reduced a bit. We've got a little bit more efficiency. Higher efficiency and lower stack temperatures are very closely related. And we're still looking to keep that draft manageable. So we're looking for O2, and I think I got an extra 0 in that O4 there. Just notice that. But it should be 0.02 to 0.04. And again, we're looking for 100 parts per million undiluted carbon monoxide. And I'll answer this question before it gets asked, and it probably will get asked. What's the difference between diluted and undiluted? Diluted is when you have a boiler or a furnace with a boiler with leaks between the sections. You're diluting your sample. You're bringing in excess air. Undiluted is when you have sealed combustion, where you're bringing in air from outside. It's not interacting at all with the air from the dwelling, from the basement. So diluted is when you're adding in air from outside sources. Undiluted is when you have sealed combustion. I know I was guaranteed somebody was going to ask that question, so answer it before it's asked. With condensing gas equipment, now we're into the 90 plus. We're getting up into the high efficiency numbers now. 88 to 92 is pretty typical. I know they all say they can get 97%, 95, 97%. You're not going to see that when you're doing testing. You're going to see these kind of numbers, 88, 92 maybe. You might get it low 90s. You're just not going to see 97. That happens in the lab. Oxygen 5 to 7. CO2 going to be ticked up a little bit higher, 7 to 8.5%. Stack temperature way down there, less than 125. Why? Because we're condensing. We want to condense, so we want to get it down there in those low numbers, as low as you can. Draft, you'll notice that instead of minus, we're positive. We have a plus number because it's draft induced. So we have to force this out. You're going to see force the flue gas out of the appliance and out of the building. So we have positive numbers. And again, we want to see less than 100 parts per million of carbon monoxide, undiluted, because again, we're looking at sealed combustion. Are we good so far, John? Anything, any questions coming in
Oh
on
boy,
that?
a lot of
Uh,
them come in.
uh,
Should you be able to get carbon monoxide levels down to less than 20 parts per million on newer condensing boilers? Asked Jerry Marshall.
yes, yes, you can. You absolutely can. You can get it. You can get it. You can get them down there quite low. Uh, yeah, that's very, very doable. So yes, the answer to that is yes, you can. You can get it down to those kind of numbers.
Very good. And why are manufacturers of atmospheric boilers that offer 89% efficiency, or for residential applications, even 91% efficiency, are they using a different efficiency than the commercial high efficiency condensing boilers?
Uh, well, we're looking at apples and oranges. It's two different types of technology. Uh, you're looking at, if you're looking at standard, like a boiler, you're looking at mass. You're looking at hundreds of pounds of mass. You're looking at many gallons of water versus your condensing boiler, which is very lightweight and has very little water content. So the numbers, see, the numbers that they advertise, they're best case scenarios. And I think that's, with any manufacturer, they want to make sure, they want to put out information that makes them look as good as possible.
I'm
So
shocked. I'm shocked that they would do that.
yes, can you imagine that? And I'm not saying that they're telling the truth. They're not lying to you. They're saying that yes, this equipment can get up to a number.
Keywords.
There's the key words, up to a number. And they're telling the truth. It'll get up to that number, just won't do it in your house.
All right. Here's
That's,
a good one from Willie Millard. Do you trust taking combustion out at the exhaust pipe? At the out exhaust pipe, it says.
you mean outside of the dwelling?
Willie, why don't you? Do you mean outside, Willie? Why don't you, if you could clarify that, and we'll come back to you if that's
Yeah.
what you mean.
What does he mean by outside?
Yeah. Here's one more from Edwin Gomez, and he says, "Sorry to make a rookie question, but what exactly is draft? Could you give a quick explanation on that?"
Oh,
Willie,
sure.
for
Draft,
Edwin, rather.
it's the movement of a column of air or gas. It's how much, it's a measure of the movement of the flue gas that's going up the chimney. And whether it be a chimney or just a draft induced flow, you're measuring the flow of the flue gas. That's what draft is. And again, you want to keep it low because, as I said earlier, we want to keep the flue gas in the appliance as long as possible. So by reducing the draft, we slow it down. Chimneys are natural draft appliances, and chimneys are going to draw simply because warm air or flue gas rises a lot faster than cold gas. So warm air rises, warm flue gas rises. So it's going to move through the appliance. And again, a draft regulator is something, it's subtracted. And what you do, how a draft regulator works is that it opens and closes. It's all barometric. It's got to do with the amount of the draft that's moving by it. And it'll open and dilute some of that, bringing in air from the surrounding, from the room, the ambient air from the boiler room, and it'll slow that draft down. So it's not a rookie question. It's a good question. It's
Good question.
a measurement of the flow of flue gas.
Okay, to all you guys have asked questions, these are awesome questions. I promise you we'll get to as many of them as we can. I want to have Bruce get back to the presentation, but I know there's a lot of questions out here that we haven't gotten to yet, and I promise you that we will. So continue.
Okay, that brings us to oil power burners. And again, same kind of numbers. You'll see are pretty much across the board, 4 to 7% oxygen. You'll notice carbon dioxide, CO2, is a little bit higher. My suggestion with oil has always been to keep it. I don't think I'd even go to 12.5%, but that's as your drop dead max. I would not even consider going any higher than that. And you don't want to go below 10. So 10 to 11, 12.5%. Problem is, if you go to, you can go to 13%. You can absolutely get it to 13%. But problem is that things are going to change, and the cellars are dirty places, and you've got a lot of things going on in a cellar, in a building. And if you change the air, you're on the edge, 13%. You're right on the edge. You're teetering on the edge. And yes, you've got great efficiency, but if the air changes the slightest bit, and that could be a little cat hair that's on those air gates, that could be a little dust, it could be a little lint, you have just gone over the edge. And now you're to the point of making soot, and that will happen quite rapidly. So my suggestion has always been not to adjust too high. That CO2, keep it under that 12%. 10 to 11% is really good. Stack temperature, remember I said that low 300s, that 325 is, don't go lower than that. And of course, 600 is a little on the high side, but that's not uncommon. And then -0.2 to -0.04 on your draft. And less than 50 ppm on your carbon monoxide. Oil, you really got to work at oil to make carbon monoxide. It'll do it. Any fuel will make carbon monoxide, but you really got to work at it to produce it with oil. Whereas with gas, it's you don't have to work quite as hard. Gas-fired power burners, 3 to 6 on O2. 8.5 to 11, pretty much the same parameters with gas power burners. They work very much the same, just a different fuel. Your numbers are pretty much the same on your stack temperature. Draft pretty much the same. Draft can be positive pressure. It depends again on the appliance. I have one of these in my boiler. I have an oil boiler with that particular burner right there that you see. In my boiler, and my efficiency is okay. I'm pretty happy with it. I'm getting about 82%, and I'm happy with that. I can certainly live with that. I would probably be getting pretty much the same numbers with oil, so I'm very happy with my 82%. And I show 100 parts, less than 100 parts per million diluted, again because I'm in a negative draft boiler, so my flue gas is going to be diluted at some point. It's not sealed combustion. While we're on the subject of carbon monoxide, I guess really gotta what is it, and why is it so dangerous? Well, it's dangerous because it's odorless, colorless, and tasteless. So you don't even know it's there. It just kind of sneaks up on you. It mixes very well in air, and it doesn't stratify, which is one of the things that makes it so dangerous, that it will follow the air flow in a structure. It's not heavier, it's not lighter, it's the same weight as air, so it'll just follow the air in a dwelling. And it's poisonous, so all kinds of bad things. It originates from incomplete oxidation, incomplete burning of your fuel. Very dangerous. Because it prevents the absorption of oxygen in the bloodstream. You basically go to sleep. You just doze off, and you just don't wake up. I guess there are worse ways to die, but you just doze off. One of the symptoms of carbon monoxide poisoning is flu-like symptoms. Slow carbon monoxide poisoning. You don't have huge levels in the house, but it's there, and you seem to be sick. You feel headachy. You have body aches, and you go outside for a few hours and you feel better, and you come back in the house and you start feeling it again. That's a symptom of slow carbon monoxide poisoning. Improper venting, fuel-rich mixture. All these are reasons for CO2, but it is deadly. You can, most of your equipment, your combustion testers have the ability to analyze ambient air. And these are some parameters for action levels in buildings. If you walk in, the fire departments all have these. They walk in with the sniffer. 1 to 9% parts per million fine, no problem. That's very normal. 10 to 35, well, there's something going on. Let them know, maybe ventilate the house, open some windows, find out what's going on. That's kind of elevated. Uh, Anywhere up to 100, it's too much. Find out what's going on, ventilate, and a medical alert. Let somebody know what's going on. There's a problem there if you have up to 99%, 99 parts per million. It's excessive. 100 to 200 is dangerous. Get out of the house, call 911. And then anything over 200 plus is really dangerous. Evacuate the whole building, look for symptoms, and call 911. These are some kind of numbers that you can find out yourself. You walk into a situation and your analyzer is going to tell you exactly what you're walking into. Let me look at the time here. Oh, wow, look at that. That's just about an hour. So I think that's all, folks.
I love it.
So
I love it.
I'll be here. I know there's some more questions. So
Oh yeah, we have a boatload here. This is fantastic. Great questions, guys. Really do appreciate it. So we'll start. Our man Rick Mayo. Where does a CO detector belong as far as elevation from the floor? If you have a carbon monoxide detector in your home,
that's
I
interesting.
usually see them on the ceiling.
Yeah, the carbon monoxide detector, you're going to have one on the ceiling, usually one over the boiler, one at the stairs, the bottom of the stairs, and then you'll have them upstairs in the dwelling. You'll have one on each floor. Yeah, obviously, it starts in the basement. And again, as far as your own equipment, was that the question? Where should your CO2, your
Yeah, if you have a
analyzer
CO2 detector, where does it? I'm guessing it means a CO2 alarm or alarm or like a smoke
okay.
detector.
Well,
I'm
okay.
thinking
If you're on a CO2 detector or alarm, which you can buy pretty much anywhere, hardware stores. With gas, it should be hardwired above the boiler, so it's hardwired into the system to shut the system down if the CO reaches certain levels. On the wall at the basement stairs, and then at the bottom of each floor, on the ceiling of the first floor, and then again on the second floor. You want it to start off with the source. The source is in the basement, and then work your way up. If it by the time it gets up to the first floor, if it goes off, get out of the house.
Yeah, yeah. What does too early cooling of flame mean relating to carbon monoxide? This is from Nicholas Toman.
Okay, that raises the level of the carbon monoxide. Again, everything is related to temperature. So by cooling the flames down, you're cooling the flame down. Let me see. How could I? All right. Here's a pretty good example of that. You've got a fire going, just a fire in the fireplace, and you've got a nice blazing fire going. Everything is working out fine. It's very nice and toasty. And then the flame goes down, the fire goes down, and you have burning embers in the fireplace. That's where your CO2 is the highest, because the temperature, it's still combusting, it's still burning, but the temperature has gone down and your CO levels are skyrocketing at that point. That's where a fire in a fireplace is most dangerous from a CO standpoint, is not when the fire is blazing, but when it's just you have embers that are burning. The flame the temperature has gone down and the CO levels have gone up.
Gotcha.
I think that's the best analogy I can give to that question. I hope that works.
All righty, but just tons more. What can you use a barometric damper on a positive pressure flue?
No, positive pressure flue. No, because the barometric is going to open, especially a double swing. No,
Right.
positive pressure. If it's positive pressure, it's using a fan to force the products of combustion out. So a barometric damper is counterproductive to that. It's going to open up, and you don't keep in mind a barometric is subtractive. It's a subtractive device. And that's the last thing you want if you've got positive pressure. If you've got positive, you want to keep, you're forcing the combustion, the flue gas out, and you're kind of counterproductive to open a door in the flue.
All righty. The values you used for some of your sample combustions, were they for steam or just for hot water, or does it matter?
Oh, it doesn't matter. The medium is irrelevant. It's the testing is the same. You're going to use the same numbers no matter what it is, whether it's steam, water, or forced hot air. You know, we're not. We don't care what the medium is. So it doesn't.
All righty.
No, it doesn't. Yeah, but keep one thing in mind though. Steam boilers aren't particularly efficient. They're just,
Yeah.
you know, they're just not compared to water boilers for several reasons. You've got to it's different technology, so they're not greatly efficient, but they're okay. I mean, by today's standards, I have a steam boiler in my house. It's 2 years old. I get 82%. I can live with that. If it take the same boiler and make it a water boiler, I could probably get it up to 85 or 86%.
Very good. What PM should be done on the double wall vent pipe? PM, I'm guessing he means preventive maintenance. This is another one from Willie.
Double wall vent pipe. Geez, I don't know. It isn't the type of thing you take apart. I don't think there's anything you have to really do to it. You don't. Double wall pipe is pretty well secured. You're looking at zero clearance double wall pipe. It's not like single wall flue pipe where you, on older appliances, you might take it down and clean out the pipe itself. Double wall pipe generally is all fitted together and you don't take it apart. So I don't see any maintenance on that unless of course it got plugged up with soot. But other than that, I don't think there's anything, you know, if you're doing your due diligence and doing your testing and everything is fine, there shouldn't be very much in there.
Very good. Can we review the type of sensors for CO and CO2? Some sensors have shorter life than others and need to be serviced or replaced. Which ones give you the lowest cost of ownership? This is from Ernest Penzenstadler.
Geez, that depends on the manufacturer. The one thing I've found though is the life expectancy of the O2 sensors is longer the more testing you do, which you know that doesn't seem logical, but it's the truth. The more testing you do, the longer it lasts. But they're all different. I mean, every manufacturer is different as far as their life expectancy and what you have to do to have it replaced. Some are field replaceable and others are not. So it depends on the manufacturer. And again, some of them you have to send back to the manufacturer to have calibrated. I would say at least on a yearly basis, at least once a year, some of them need to be recalibrated, which means sending it somewhere. And I said early on that I think that you really need to, how fast can they get it back to you?
Yeah. Oh, I told you this was going to happen.
She waited a long time though.
She is like clockwork. Right at the very end of any webinar we do, that's when she feels like barking.
The dog knows how to tell time.
That dog is like clockwork, I'll tell you what. Is there a code requirement for a boiler kill switch to disable gas-fired boilers for residential and/or commercial mechanical rooms?
Kill switch? Well, I know that the CO detectors can be hardwired into the boiler if the CO detector goes off to shut the boiler off. Whether that's a code requirement, I'm not sure. I think it is similar to your firematic controls that you had with oil burners. I think it is a code requirement.
I think that would depend on where you're at, right? Most likely.
Yeah. I mean, it's different states and have different requirements. So it really would depend on where you live.
And
It's
here's
a good,
one from
it's a good
Patrick.
idea though.
Say what?
It's a good idea though.
It is. It always is. Yeah. Patrick Bevilacqua asks, have you ever seen where CO2 level in a residence was high, but not even throughout residence? That after clearing the house the next day, all sources of CO2 check out okay. My thoughts were possible pre-start on automobile ran in the garage, causing the CO2 as most pre-starter shut off after 15 minutes. I'm trying to decipher what you just said there. I'm guessing he was talking about carbon monoxide, not carbon dioxide.
Yeah,
Yeah.
yeah. Well, yeah, starting up a car inside a garage is never a good idea. But yeah, that would give you high readings, and for sure. I mean, I think that would probably be one of the first questions I would ask upon getting there. If, did you start a car up in the garage before I went crazy looking at all the appliances? But yeah, that's never a good idea to start a car up in a garage with the door closed. Never a good idea.
Yeah, I agree. There was one other one in here that was kind of interesting, and I don't know if it's even answerable, but let me see if I can find it. All right. Which expends less money and in which order? Natural gas, propane, electric, oil, or diesel? If a customer could pick whatever fuel he wanted.
Uh, which cost less? Was that the
Yeah.
question?
I guess which out of them all, which would have the lowest overall cost? That's always an interesting question. And I guess it would depend on, if you're in an area where you have an electric co-op and you're paying 3 cents a kilowatt hour, well, that's pretty easy, right? That's an easy,
Yeah,
get an
yeah,
electric boiler and call it good.
that varies from, again, depending upon where you are. I mean, it's like up here in the Northeast, electricity is pretty expensive. Uh, Geez, I go to Florida in the winter and electricity is really cheap. So it depends on where you are. Uh, if you're comparing, geez, the fuel oil, I haven't had to deal with that in several years. I know for years oil had quite an advantage over gas, and then natural gas, and then that flipped around. Uh, that it changed, and that the price of natural gas came down, and the price of fuel oil went up, and then the biofuel came in, so that caused the price to go up even more, and then things are very fluid as far as prices. It kind of depends upon what's going on in the world. Like right now, gasoline is incredibly cheap. Why? Because nobody's driving anywhere, which is kind of ironic because gasoline is very, very cheap. So I don't. I would say look at
It
what you're
depends.
paying for BTUs. It really comes down to that, because it's all about BTUs. What are you paying for BTU?
Right. Right. Is there a combustion analyzer that works well with smartphones? I find the printer on the back rack ones are a hassle. It would be nice to share a report via email with a customer or for my records. Our company doesn't have multiple analyzers yet, and I'm trying to stress the importance of having them for tankless and boilers. So do you know anybody that work well with smartphones?
I know Wohler does. Wohler has one that works on Wi-Fi. I don't remember the model. I had a picture of it. It was one of their higher end models, but it works on Wi-Fi. It'll communicate with a smartphone or through the internet. So I know for a fact that Wohler has one. I'm not
All right,
sure about, yeah.
Mary Jordan says Ecom does as well.
Okay. Okay. Ecom is one. Good.
All right.
Thank you, Mary.
All right. And Nicholas Tillman has a follow-up. I guess the question should be, is there more CO possible at low fire rates rather than at high fire rates of a modulating burner, based on what you were talking about earlier?
Is more CO on
Hey,
lower than
yeah.
higher? Um, well, you do two tests. You make adjustments on both low and high. Your CO numbers obviously are going to go up a little bit when you go to high fire, but then you adjust for that at that point. So you make your adjustments on both low and high fire. So yeah, it'll go up. It would have to go up because obviously you're burning more fuel, but then you adjust it back to the levels that you want. You make adjustments in both ranges.
Now here's a question I have, and this, nobody wrote this down, but it's a question I've always wondered about. If you're installing a new boiler in the summertime, and you do an efficiency combustion, you do a combustion test in the summertime, how accurate is that, and how does that relate to wintertime efficiency? That's a question I've always had.
Well, that's a good question, especially if your appliance is using outside air. It's going to be a very big difference. So the temperature of the air, if you've got sealed combustion and your appliance is using air from outside, and you're doing your testing on a nice hot humid day in July, you're going to see very different numbers if you do when you do a test on a cold day in February, because the ambient temperature is going to be different. Remember that it's all about that net temperature, so that's going to be very, very different. So your numbers are going to be different from a test in the summer as from a test in the winter. Your numbers are definitely going to be different. Whereas that's only if you're using outside air. If you have sealed combustion. If you're using the air from the dwelling, then there's virtually no difference. I mean, it's negative.
But you're still looking for those same percentages on CO and excess air, et cetera, right?
Yes.
Or CO2 and excess air.
Yeah. On a hot, humid day, when your air is going to be in the wintertime, your air is going to be thinner. So you want to make your adjustments a little on the lean, on the heavy side in the summer. Again, not, you don't want to be making smoke, but you go a little bit on the heavy side because you're going to have leaner. If you're breathing outside air, it's going to be leaner in the winter. So you have to look at the amount of time the appliance is going to be running versus, all right, you do your test in the summer. It's heat only. It's not running for heat. When it does, when it's going to be running most of the time is in the winter, when it's going to be burning that leaner air. So you want to make your adjustments based on how the amount of time it's going to be running most of the time, which is the winter time.
Right. And if you throw a combi into the equation, then or a tankless, well, a tankless is going to be running the same amount of time, winter or summer.
Yeah,
and a combi, same thing.
Yes, that's not the same, because now it's going to be running all the time. It's going to be running 365 days a year. So you pretty much, and again, I think I would go the same route. I would adjust it like it was the winter, because again, look at how much time a combi runs on any given day in the summer versus how much it's going to run in the winter. It's still going to be running a lot more in the winter than it's
right. That's true. That's very true. Yeah. One last question came in here from Ron Anastasi. Some boilers, Utica, Dunkirk, Viessmann, as examples, can actually monitor combustion characteristics and constantly adjust CO and CO2. So seasonal combustion efficiency will remain stable and fairly constant. So they kind of work together there, and that's good. That
is I think that's a great idea, because again, it's like the self-driving car. I think we've come a long way with our equipment. I think it's a great idea that the boiler will adjust itself based on that. And again, this is looking at outside temperature. The temperature is going to change of that air that's using for combustion, which is going to change the numbers. And if the boiler can adjust itself, that's great. That's great. It's a great idea. I love it.
Excellent. Jeff House says, as always, follow the boiler and tankless manufacturer's recommendations, which are the.
Oh, you mean not as a last resort?
Yeah. Okay. We call that RTFM.
Hi, Jeff.
The RT and M is read the manual. You can fill in the blank for the other one.
Yeah, it's not a kneeling pad. It's
right.
Read the instructions. Jeez.
Read the instructions. There's so much wisdom in the instruction manual. Have you ever noticed that?
It's amazing. The people that they put all this stuff in there, and if you just read it, it's everything you need to know.
And it's free. They
It
give
is.
it to you for free. All righty. Richard asked, we'll be sending copies of the audio and PowerPoints. Actually, we're not allowed to share the PowerPoints, Richard, but you will get a copy. You will there'll be a follow-up email sent to everybody tomorrow with the certificate of attendance and also a link to view a recording of this presentation. So you'll be able to go back and view it as many times as you like. Okay, so that'll be sent out. That'll be sent out to everybody tomorrow.
A
So
PowerPoint, so they'll be able to see the PowerPoint too.
yeah, they'll be able to see the presentation, the complete presentation. It'll be all there. It's and then it'll be in the form of a live recording. Yeah.
Oh, and I can take notes.
There you go. You can take notes yet again. There you go. Oh, you got a lot of fans out there, Bruce. Thank you. It's good to see you again. Excellent presentation and training. Well done, as
Well, thanks.
always. And you may be retired, my friend, but you have left a definite impression on our industry. So it was a pleasure to share this day with you.
I've loved the last 2.5 years. It's been great. I've been enjoying my retirement, but it's also fun to put my toe back into the pool. I'm not jumping back into the deep end, mind you, but just to step my toe back into the pool. And I've always loved doing this. I've always loved sharing what I've learned all these years, and it's great to do. And I thank you for the opportunity, John. This is I love doing this. I've enjoyed it, and down the road, you know my phone number. So
You got it. Would you guys like to hear more from Bruce? Because actually, Bruce came fairly cheap. All I had to do was offer him a free round of golf somewhere. So he can be had fairly cheap.
yeah, it's not about money. It's about quality of life, John.
There you go. There you go. So we will go play golf someplace very, very nice.
I can't wait. I am
And you'll
dying
give me
to
3 strokes aside, right?
give you 3 strokes. Yeah, I thought you were going to give me 3 strokes.
Hey, I got to start the gamesmanship early, my friend.
Well, I'll tell you, I played twice a week in Florida while I was down there, and things started coming together.
Oh,
And then I had to come home.
now, you might kick my ass yet, because I'm still struggling on which end of the stick to hold, quite frankly. I've had a rough spring.
Well, I got the driver going pretty well. The putter's going really well. The fairway woods are going pretty well. I'm okay up until I get to a chip shot, like 100 yards from the green. That's when I get into trouble.
Oh boy. Yeah. Well, my driver is going. I'm long in every direction. All
Oh,
right. If it's straight, it's long, but if it's dead left, it's really long, right? I'm at and it'll go in any direction.
uh-uh.
Irons, putting, forget it. Chip, short game, forget it. I'm a mess.
Uh-oh. That's what's so much fun about the game is you just never know.
That's it. That's it. And hey, and you know what? If we had to do that for a living, we'd have skinny kids.
Oh my goodness, yes.
All righty.
Fortunately,
Well, thank you.
you'll never see us on Saturday afternoons on TV. So,
No, not on golf anyway. All right.
oh, goodness.
Well, thank you so much again, Bruce, and thank you to everybody for joining us. It was a pleasure to have Bruce with us, and really appreciate the gift of your time, folks. And we shall see you down the road. Take care, everyone.
Thanks, John. Goodbye, everyone.